Hi all. So we're going to move into the last section from your unit number 4, and also this will be actually the last section for your whole semester also. So under this section, I'm planning to discuss about the wave nature of light. So you know that we discussed this earlier too, but this is where that I will plan to discuss little more detail. But it is very important that we are doing it very conceptually, because this will be another class starting at this point and forward. Okay, but I'm planning to discuss very briefly for your class because I hope it will be helpful for you to understand some of the things happening in our real life. So again, there is no experiment that you are going to do for your class in this section. Okay, so now we know that the light carries the energy, as we discussed, right? So since energy can be carried from place to place, basically by using two ways. One is the particle nature of the light, and second is the wave nature of the light, right? So particle nature of the light was identified or discovered after identifying of the light as an electromagnetic wave, because light is, you can explain like your refraction, reflection things by using particle nature of the light. But light has a wave particle duality. So that is the basic part that we're going to do it in here, especially by using the scientist principle, Huygens principle. Okay, Huygens is the name of the scientist. So now in this chapter, it is actually, let me share it first. So your chapter will be chapter 27 in your textbook. 27 in your textbook, right? So basically these are the parts that I'm going to cover: interference, diffraction, double slit experiment, little bit very conceptually, and then little bit about the Huygens principle. Okay, so now let's move into the chapter. Okay, so now light as a particle or as a wave, right? So Newton was famous for many things. Actually, throughout the semester we talk about his discoveries, but one of the most important things that he discovers is about the light, right? So he discussed about the light as a beam or like ultra tiny particles that going from one place to another place, right? So now by using this particle nature, we will be able to show the reflection and refraction that we discussed in your section number 1, unit 4, right? But some other things were not able to explain by using this particle nature. So example is interference and the diffraction. So now to explain those, we need the wave nature of the light. So that's where the Christian Huygens is the scientist described about the light waves spreading out from the point source and it's overlapping and creating the secondary wavelets, and it's keep moving. What that means is basically, you see that in here you have source, and source, and this source is creating the light, as we know, right? Those are, we call it as the wave fronts that create by the source. So now after it go to the next place, you will see that this all the wave fronts will create a kind of, we call it as secondary source. This all the lights will spread out, then create a next source, but that source has many sources, right? Then it will create the light, and then it will go to the next wavefront, next source, and that's how the light will going to spread out. So now those we call it as the wavefronts, right? So that will basically saying that if you have a single light, that will create a kind of next source by emitting the wavefronts on all directions, right? That is what the Huygens found out, right? So after that, we were able to describe some of the other things, so especially diffraction and interference. So now let's go to this chart, and we know that the reflection and refraction will be able to explain by using particle nature of the light, right? It doesn't matter. You can also use the wave nature of the light. You still can identify, or you can describe the refraction and reflection, right? But next concept, you have it in here: interference, diffraction, and polarization. We know that we discussed about the polarization. Polarization is not able to describe by using particle nature. You remember that electromagnetic wave hit the media, then one light will refract and one light will be reflect. That reflection will polarize only the electric wave, as you remember in Brewster angle that we discussed. So that polarization only can describe by using the wave nature of the light. Okay, so polarization only work with the wave nature, not able to describe by using particle nature. And diffraction and interference is the new thing that we're going to discuss today. These two always work with the waves that you can describe. Particle nature will not explain those phenomena. Another one is the photoelectric effect. Photoelectric effect, by words, it's actually only the particle nature. So it will not be able to describe by using wave nature at all, right? That means wave nature will work for all except photoelectric effect, but particle nature will work refraction, reflection, and photo effects. Okay, so now 2 words: diffraction and interference. It's very easy to understand. Diffraction is saying that it is actually bending of the wave due to obstacle or due to some disturbance of the setup. It's not because of the refraction. Refraction also like bending, but that is not belong to diffraction. Diffraction means bending of light due to some kind of obstacle or some kind of disturb that will disturb the traveling of the light. Okay, that is the diffraction. So now interference is basically overlapping of waves will create, they will combine together, create a constructive, or they have opposite direction, then they're going to create a destructive interference. Okay, so that's we're going to discuss. Okay, that basically superposition of the waves called as interference. Okay, so now again to get an understanding between wave and particle nature. So now particle usually have a particle behavior that has a kind of linear momentum, because it will move in with velocity. In your 116 class you discuss, it is moving with the velocity, and mass and velocity, these together, we call it as the linear momentum. That's the particle nature of the any particle, right? So it will have a momentum basically. Now, if it is a wave, so there is a not the momentum, but there is a wavelength. We call it as de Broglie wavelength. So that will be defined as h over p. P is, as you know, it is momentum, but h is, we call it as the Planck constant, right? So that means when the particle moving, that particle has the linear momentum, but when the wave moving, it has the de Broglie wavelength, depend on the h and the ratio of h and the momentum ratio. Okay. So now let's move into the photoelectric effect and quantum scattering. As I discussed in the earlier chart, photoelectric effect is a particle nature of the light, right? So simple example, protons are particle, right? Photons means basically light waves. So when the photon hit the metal, this is the physics behind the solar cell kind of things. So photons or light going to hit the metal piece. Then if that photon has enough energy to produce or to absorb this metal, and then basically the electrons will be able to energize. I'm sorry. So they will be going to escape because of getting energy from the photon, that will be the emitting of electron. So when the photon hit the metal, the electron going to have some energy. If that energy is enough for them to escape out from the metal, then electron will be emitted, right? This thing happening if photon has enough energy. If it is not enough, then this will not happen. That's why when the sunlight is there, then photon has enough energy to emit the electron. That is, we call it as the photoelectric effect. This was get the Nobel Prize again, Albert Einstein, 1921. Okay. So now next one is the quantum scattering. Quantum scattering is similar to the usual scattering that we discussed about collision of two objects, right? What is happening is you have a photon, light again, come in and hit the electron. Then we know that when I have electron and proton hit, then this will choose the direction and move in different direction. Now this is, we call it as scattered proton. This is called it as scattered electron in different direction according to the velocities they have and masses they have. They're going to choose the direction after the collision. That is called it as quantum scattering. Okay, so now let's move into the interference and diffraction. Right. So as I mentioned earlier, Huygens is the scientist talk about this light is traveling or propagating as a wave, or it will propagate, create a next source, a multiple next source, and keep spreading the lights to the next source and like that. So that will travel with the speed of the light. Right. So now interference pattern. What is the interference means? Basically, they will overlap the light and create the pattern. Now, simple example is if you think about the, you have a very simple, very small two holes that you're going to project the light on the dark room, then you will not see the two dots on the screen on the back. You're going to see a lot of holes, or a lot of like a pattern of holes on the screen, because this light is not like traveling two lines. It will travel as a wave, then they will combine, interfere, and create a fringe pattern on the screen. That is, we call it as the interference. Okay. Okay, so now that I have something weird in here. Slide. So now interference of the light waves, they can create constructive. That means they're going to combine and create a high intensity. Simple example, if you think in this wave, there is a height, this one, we call it as amplitude, right? So now this one is another wave that has again amplitude almost same amount. So now your resultant, if the overlap of first wave and second wave, they're going to create an amplitude double of the amplitude we had in single wave. So that is, we call it as the interference, or constructive interference will create a brighter light than you send, right? So now destructive interference can happen. If I have this one, you see that it is some amplitude, but exactly that time interval you have a backward amplitude. Now you have one up and one down. The combination of these two will create, if they are exactly same, you will see the very, you will see no light at all. We call it as completely destructive. But if one is greater than the other one, you may see very small light. We call it as dimmer light or dark light. Okay, so that we call as a destructive interference. So now, because of this constructive and destructive interference, what will happen is when you send the light from the slit, so that will create a pattern, that is, we call it as interference pattern. Okay, so now let's move into the diffraction of the light. So diffraction of light, as I mentioned earlier, because of bending of the light. So diffraction can happen even from the single slit, right? So now if I have a single slit, compared to these numbers, this thickness, the thick, the slit size is very, very small. Okay, so very, very small. You see that it is around, it says 6 times lambda. The wavelength is in measuring from a very, very small scale in nanometer region. So now if you have a single slit, if you send the light incident wave, so that will create a diffraction wave. It's not create exactly same way, but it will create a kind of diffraction that because of the bending behavior. So now if you make it, you see that it's getting, slit is getting smaller and smaller. When this slit is very, very tiny, then you will going to see a nice diffraction pattern on the screen. So that is called it as the diffraction. So now I have it in here. This is actually happening because of diffraction, and this is actually happening of interference. You see that waves are interfere, right? So now if I have a screen in here, this is what you're going to see it in the, if you do the experiment in the laboratory. So you're going to see fringe that has dark and bright spot. I'm using red light, because of that I'm going to see the red. If you use the blue light laser, then you're going to see the blue. So this will be the pattern that you're going to see. We have very bright in the middle, and then you see some order you will going to get, and then intensity going to be lower and lower when it's going to further away. But that's the pattern that you're going to see, right? So this is definitely happening because of the interference. When we have constructive interference, they will create a brighter dot, and when it is destructive interference, that will be the dark fringe. Okay, that's how it will happen. Okay, so now this is for you to observe it again. So if you have different lights that will say I'm going to use the green light, then the red light, green laser, or red laser has the pattern that green laser also has the kind of that. But the since they have different wavelength, you remember the red has the higher wavelength than the green, right? Because of that, you're going to see the separation distance is different of your pattern. So that will be easy for you to identify some important informations. Even wavelength of the light you will be able to find by using this pattern. So that's the experiments that we basically doing for third level of physics. So now in addition to that, we are doing sending white light also. When you send in the white light, because of color spectrum, white light is a spectrum of colors in the visible range. You're going to see not a single dot with the single color. You're going to basically see in the middle white, but then you're going to see the spectrum of colors, right? Not the dots. You're going to say spectrums of colors throughout moving towards up and down in this case. Okay, that will be basically the interference if you use the not probably single, not probably double slit. So you can use the grating for that. Grating means many slits, right? Per millimeter, I have 600 slits or something like that, right? So that will be create a very nice spectrum that we can easily measure the distance in between those. Okay, so now I know that I discussed about the constructive and destructive interference, but this is more detail about that. So now if I have two slits, right, S1 and S2, if I send the light, we'll say this is a D distance, right? If this D distance is much greater than the slit separation. Slit separation means distance between these two. This is the D, okay, slit separation. If D is much greater than this D, you can say this is basically derivation of that. You can say this R1 and R2 are parallel to each other. This is the zoom in picture of that. R2 and R1 rays are parallel to each other, right? So now if I draw this diagram, you're going to see this green color line that I have it in here. This line, this distance is the difference between R1 and R2. That is, we call it as path length difference. Path length difference. That is the different length difference between R1 and R2, right? So now that length, definitely I will be able to calculate, since I know this angle, if I am able to measure it, if this one is D, then this will be opposite. That means that will be D times sine of theta. This length is D times sine of theta. It is the opposite length of the angle. So now this is what it goes for you to create a dark and bright fringes or constructive and destructive interference. So now if this D sine of theta is equal to a wavelength, that means you will create a wavelength like this, or you can create double wavelength, or you can create triple wavelength. If it is going as a number of wavelength 0, 1, 2, 3, 4, that means this kind of pattern, that will create a constructive interference, right? So now, but if it is a half wavelength, that will create a destructive interference. In that case, your formula will be changed into this formula. So that is the constructive and destructive interference, how that's going to happen, right? So I have this formula in the bottom that will show you the constructive and destructive interference, that you're going to see it on the diagram on the right side. Okay, so right side in here. Okay, so now again little more details. By using grating, by using white light in here, you will be able to see a spectrum which is in different order. This M number that I mentioned, this is, we call it as the order number. Order, that means the your first one is M equals 0, M1, M2, like this. If it is the first one is this one, this is M equals 0, this is M equal 1, like that. Okay. Okay, so now let's move into a little bit about the diffraction again. Diffraction is bending of light. So diffraction will be able to understand, you see that in here, when it go to this point, this is the obstacle that you have. These lights going to bend towards, because of the this obstacle, your light going to be bent, right? So now this light will create a bright spot if you are ending up with exactly same. That means if you're going to end up with, you say my wave is, one wave is going this way, and I have a next wave also going this way. If these two waves going to be overlap at that point, then it will create a bright spot, right? If they are going in opposite direction, then they're going to create a dark spot in there, right? So usually your diffraction pattern, the center one is the very bright point, but then you're going to see the smaller fringes after that. So this is totally because of the diffraction. Even I have a single slit, okay, not the interference. So now in this case, I know that I have a lot of formulas in there, but we are not going to use those for your class, not much important. But still you have a D sine of theta equal M lambda. Let's take a look what is the D is. D is the distance between your slit and the screen. That is the D is. Again, that you will be able to combine with the your order number M equals 0. M equals 0 has the high intense peak, and then you have the peaks that will label as dark in here. So this is the dark, this is the dark, this is the dark in multiple of that lambda over D ratio. That is how we get the diffraction pattern. So diffraction pattern will be able to easily identify if you have more slits, basically, or very narrower slits will be easy for you to, it's called as diffraction grating. You will be easy to understand or see these orders very clearly. Okay. Now, the microsine interferometer is one of the instruments that we actually use to find the refractive index of the material, phase shift, visualization of the interference, those things. This is the experiment that we can do in advanced level physics laboratory. But this is the simple thing about the the interference that we discussed, because you see that in the setup, we definitely have multiple mirrors, actually 3 mirrors, and object is in here, right? Then you're going to observe it from here by using the telescope. So there are movable mirrors, there are fixed mirrors, and there is tilted mirrors that I can change it. So this fine-tuned adjustment give you the interference pattern like this. Then by measuring distance of those bright spots, we will be able to identify the phase difference, and that will have the connection to refractive index. This is refractive index, right? So refractive index will be able to calculate by using that. Okay? That's one example. And so now we're going to move into Doppler effect. So you guys talk about the Doppler effect in your 116 classes, for especially for the sound. What is the Doppler effect is? Doppler effect is basically happening because of the frequency change. That if you have a fire truck here, if one student sitting in very close to fire truck in this side, then you're going to hear the frequency. But when you move away from the source, if the fire truck is still at rest, then you're going to hear the lower frequency, right? That is one way you can do. And in addition to that, you can, fire truck can move towards you. So that relative motion will create the frequency shift. That is what we call it as the Doppler effect. That will be the same for the sound, light also, right? So now in light, it's what is happening is there is different places in the source. You see that the source is moving towards the lady on the left side, but source is moving away from the observer in the right side. Now what is happening is because of this motion of the relative motion between observer and the source, so now the lady on the left side going to see the blue shift. Blue shift means, because you know that in the spectrum, blue light have higher frequency. So because of that, you're going to have the higher frequency herein, because your source is coming towards you. That is the higher frequency that you're going to have. Because of that, that is, we call it as the blue shift, right? But one is on the right side going to have the low frequency. So that will be a red shift. So that red shift for the right observer and left observer, it will be the blue shift. So that's very important thing, especially when you go to the astronomy part, that we know that the galaxies, stars, and this all are distance away, and they are going further away from the Earth, because we're going to observe the red shift as always. That means it's a signal that they are going further away from us. Okay, red shift. Okay, I think that's it for this chapter.